Okay, today we're going to complete our videos on the Standard Model, and we're going to end with looking at how do particles interact. So let's consider what this problem entails. So we've got the Earth here with our very inaccurate country, so this is our Earth, and over here we have the Sun. We orbit the Earth, we're held in place, there's an attractive force of gravity from the Sun's gravitational force pulls the Earth, and also the Earth exerts a gravitational force on the Sun, and that's what keeps us in orbit around the Sun. How does the Earth know the Sun is there, and how does the Sun know that the Earth is there? They're not in contact. How does matter know each other exists? The same problem exists with charged particles. We could have a positive charged particle and we have a negative charged particle, and they're going to attract one another. How do these charged particles know the other one is there? Similarly, two positive charged particles are going to repel. How does that force? How do forces transmit that information? Seeing that there's no contact between these different bodies, how does that actually happen? So this implies that there must be particles that interact to carry forces. Now the Standard Model has 4 types of force, and non-contact forces. So forces that act over a distance where there's no contact happening between them, that the particles aren't crashing, smashing together, and then coming apart. So these 4 forces are called the nuclear weak force, the nuclear strong force, electromagnetism, and gravitation. So each of these forces have different force mediating particles. And we call these force mediating particles, they belong to a group of particles called bosons, and specifically we call them gauge bosons. So let's consider how this would work by having 2 hypothetical particles. So I'm going to get the colours out so that we can. So let's have this particle here, some big particle. Remember when we're talking about things about the atomic and nuclear level, something that we could is really small, but at a nuclear level, this could be really big. This could be like a proton, which would be massive on a nuclear, is a massive particle on a nuclear scale. And we'll have another particle here. I'll just give it a darker colour. It's not much darker, but never mind. And we'll call that particle B. Now, particle A emits a gauge boson. Nope, meant to have changed colour. Here's our gauge boson, and it goes to particle B. Now, as this impacts particle B, there'll be an impart of momentum. So we're going to have an impart of momentum. So think back to our studies of mechanics and conservation of momentum. In addition, as the particle A emits this gauge boson, so this is our gauge boson. Particle B is going to recoil. And this is because of conservation of momentum. What we see, this looks like particle B is repelled from A. So the gauge boson is released, this imparts momentum to B, B then recoils because of the conservation of momentum, but what we see is A and B having this repulsion from one another. Now, let's have another particle A and another particle B. My colours have no meaning whatsoever, I'm just picking them at random. This time, let's say we're going to show how an attraction would happen. So attraction happens if we have the ejected boson in the opposite direction. So the boson is going to come out here in the opposite direction. So here's our gauge boson. And it's appears to be absorbed in the opposite direction, so that now you're going to have the particle B moving towards particle A, so it has the effect of an attractive force. And again, this is so the gauge boson is still imparting momentum, but now because it's in an opposite direction, conservation of momentum, the directions are reversed, so you now have this movement in towards A, and this would appear to us as an attractive force. Now this seems really quite strange and bizarre and quite difficult to understand. This is a highly simplified explanation of what's going on, And what particle physicists have been looking at this for years. There's been many experiments. They've refined this these ideas and analysed their findings, and this comes out of all that work. As you go on to study physics more, you'll see this in a more sophisticated and elegant way. Now, let's have a wee look at the Standard Model and where these gauge bosons come into. So, we have our quarks, so our up, down, charm, strange, top boson, and these make our hadrons, and we have our leptons that are associated with our quarks. We've got our electron, neutrino, muon, neutrino, tau, neutrino, and then we have the same in antiparticles. Now here are our bosons, our gauge bosons. So we have a gluon, a photon, a boson, a W boson, and a W minus boson. These are all our bosons. And these are what are associated with our fundamental forces. We also have the Higgs boson, which is a gauge boson, a scalar boson, sorry, which is responsible for how we perceive mass. It's what gives matter its mass. We'll come back to that after. Let's look a bit more at how which bosons here are responsible for which force. So we have our strong force, and we'll have the relative strength. The strong force is the strongest force. Relative strength 1. Now the range of these forces in meters varies considerably between the different forces. So the range of the strong force is 10 to the minus 15 meters. So this is only acting on a nuclear scale. It's only in the nucleus. Out with the nucleus, the strong force basically doesn't exert anything. It's as if it doesn't exist, and that's why it took such a long time before physicists even knew of the strong force's existence. The gauge boson responsible is the gluon. Now the gluon sounds like glue, and from that that gives us a wee hint as to what the strong force is all about. The strong force holds together the nucleus, so it's an attractive force between hadrons in the nucleus. So it's the strong force that is responsible for keeping the nucleus together. So if you've got two protons, the electromagnetic force is trying to push them apart, but the strong force holds them together. So that this also tells us, because of the range, there is a limit into how big a nucleus can be. The nuclear limit is 10 to the minus 15 meters. Because anything bigger than that, the strong force won't be acting, and the protons will start to, the electromagnetic forces repelling the protons will take over and they won't stick together. So the gluon is the gauge boson of the strong force. The next, in strength, the next strongest force is electromagnetic. And its relative strength is 1 over 137. Its range is infinite, and the gauge boson here is the photon. The next is the weak force. The weak force is not the weakest force. Its relative strength is 10 to the minus 6. And the weak force is something that acts over even smaller ranges than the strong force. It's 10 to the minus 18. And the weak force is linked to nuclear decay. So you've got the W plus boson, the W minus boson, and the Z boson are responsible for the weak. The gauge boson responsible with the weak force. And finally we've got gravitation, the weakest force of them all, but ironically the one that holds the universe together. The range here is infinite, and gravitation, the graviton, I'll rewrite that because it's messy, you can't see it. The gauge boson is a graviton. I'm putting a question mark here because it has still, this is a predicted particle. This has not been observed in any experiment, and the hunt is on for the graviton. Since every other element of the standard model works beautifully, and it is a fundamental force, and as I started by saying, how does the sun know that the earth is there? There has to be a gauge boson for this force to exist, because we see the results of gravity everywhere. The graviton therefore must exist. It just hasn't been observed. Both gravitation and electromagnetism are proportional to the inverse of distance squared. But they act over very large distances, and these are the two that we see, that we experience in our everyday life, although we obviously experience the strong and weak force, because if the strong force didn't exist, there would be no life, because the nucleus wouldn't hold together. The gravitational and weak are of a magnitude of 33 times weaker than the strong and nuclear electromagnetic forces. The matter particles, so your quarks and your leptinos, let's just quickly nip back into our standard model. So our quarks and our leptons, these and antimatter equivalents, these belong to a family of particles called fermions, and the opposite antifermions. Force particles are bosons. Now, classification of particles, we've talked about them having their charge, they've got mass. Particles also have a property, a quantum mechanical property called spin. And this property called spin also plays a part in the classification of elementary particles. We're not going to talk about spin here, but it's something that if you go on and you're studying nuclear physics, particle physics, spin becomes very, very important. So I'm just going to put that out there so you know that there's a whole other aspect of this that is not going to be taught here, but is very, very important. I touched on the Higgs boson. The Higgs boson was like the graviton, was predicted by the standard model. They knew it had to exist. They knew what properties it would have to have, and they had a rough idea what the mass would have to be to satisfy the hypotheses that they had for it. They just had to find it. And up until the building of the Large Hadron Collider, they didn't have a particle accelerator that could generate big enough energies to go and hunt for it. So the first job of the Large Hadron Collider was to go on the Higgs Boson hunt. And it was discovered in 2013, and its mass was found to be 124.97 giga-electron volts. And it's 33, so this is 133 times more massive than a proton. The Higgs was proposed as an explanation for the fact that gauge bosons of the weak force, so these ones down here, have mass, but the gauge boson of the photon, so the electromagnetic force, is massless. This break in symmetry between the weak and the electromagnetic forces is a result of the Higgs field and is associated with the Higgs boson. So it's all to do with particles having mass. The graviton is probably going to be not very massive either. The photon basically has no mass, and the graviton would probably be the same, making it very difficult to detect. So I hope that helps.